Our next to last speaker for today is Rish. Adam, the formal one I got is Adam is a recently joined staff scientist with Sentronic US Corporation. If I would word this, I would say Adam is our last win in the US and to support our US team with his great knowledge on MVDA and chemometrics, but I didn't word it. He earned his PhD in pharmaceutics from Duquesne University in 2023 with a research background in chemometrics and PET. His current research interests are lean chemometrics and statistical modeling techniques that reduce financial costs of development and associated calibration burden for spectroscopic PET application, for example with NIR. It's even indicated here with a primary focus on NIR. Great to have you on stage. Audience is yours.
Test. There it is. I blame Brad. Yeah. Yes. I've learned my lesson. All right, we're just going to stick that in my pocket. It's too much trouble. All right, anyway, as I was saying, so bias correction and iterative optimization technology algorithms via wavelength weighting. So this is going to be a little bit more of a technical talk, but hopefully you'll find it interesting and engaging. Don't be afraid. There's going to be a lot of math, which I like, but not everybody else likes. So before we start, I'm going to give a little bit of background. Apparently there was interest. So originally I was going to apologize for repeating material from yesterday, but now I'm not going to. So calibration burden refers to the total amount of time, materials, and financial costs associated with actually calibrating your multivariate data analysis method or chemometric method. And this is a big consideration when companies are looking to implement PAT. Those costs can get really high really fast, as Owen showed earlier. So this has led to a lot of interest in what we're calling the general class of lean chemometrics. So chemometric multivariate data analysis methods described as time-saving, material-sparing, and cost-cutting strategies for the purposes of reducing the overall calibration burden of developing, validating, and maintaining an analytical method. And just to highlight, these are the same examples Owen gave, but obviously what we're going to be focusing on is IoT. But to highlight a little bit more about what calibration burden might actually practically look like, I have this, we'll say, number line with a bunch of different designations. These are different classes of models: pure component models, decomposition models, that's your PLS, PCA, machine learning, that's your AI, quote unquote, that kind of stuff. So starting at the far end, which is kind of the maximum number of samples. So the black box represents your prediction space, and the red dots represent individual calibration samples and the associated reference data. So in pharmaceutical applications, you can think of this as your mixture spectra. So when we say an opportunistic training set, you can see there's not really any structure. You're just trying to describe the entire data space. Full calibration takes advantage of calibration set structure to describe the entire space in a more efficient manner. And then when we move on to efficient calibration, these are more like your design of experiments like I-optimal, D-optimal. You're still describing the entire space, but you're using less samples. Then we can move on to partial calibration, where we're really only focusing on whatever the prediction is of interest. So for example, in a pharmaceutical process, a partial calibration might just be a series of potency steps of the API, without really too much emphasis on variations in excipients or process parameters. Minimal calibration is just what is the least number of samples we need. And so that can be as few as 1 sample. This is typically when you're applying some kind of pre-processing, you need to calibrate some kind of parameter. And then finally, calibration free, where we don't need any kind of mixture samples with associated reference data to generate predictions. This doesn't mean those predictions are necessarily correct, but we can easily generate predictions. So IoT is one such calibration-free sample, or calibration-free approach. So it's an optimization method, so it is a little bit slower than PLS, but with the right kind of optimization of your method, that is not really a problem. So IoT is focused on minimizing the difference between the true mixture spectra and a simulated spectra, and that simulated spectra is generated by adding together the pure component spectra, which is the K matrix here, in a weighted fashion, and these weights are varied over the course of the optimization. And so those weights correspond to the concentration or relative abundance of each individual component. And because this is optimization, we can take advantage of constraints. So these are some generic constraints. If you actually want to implement this method, those constraints could be anything that you could easily justify. So typical is summing all our components to 100%, and then each component only exists between 1 and 0, so we're not getting negative mass predictions. So, and of course, there's always some key assumptions associated with this, but generally, it's a pretty straightforward technique to understand, which is really appealing as a lean chemometric method. So one thing that is common in chemometrics to take advantage of is variable weighting, which is the application of coefficients to variables, for spectroscopy wavelengths, to adjust their influence on the data analysis or model prediction performance. And so that kind of gives us two effects. You can use it for downweight certain regions to do noise reduction and minimize interferences, or you can upweight certain regions to enhance particular signal and other features. So what are some of the reasons you would want to do weighting versus what are the risks? So benefits of weighting: improvement in prediction model accuracy, correction of model prediction bias, and enhancement of model interpretability. And another thing is that this is sometimes applied for model maintenance or model updates. So that's another useful application. The risks, of course, are it increases the complexity and calibration burden. So when you have to take into account weighting, you have to make sure that what your weights you're applying make sense, and you probably need more samples for that. There is a risk of model overfitting, and there is a level of subjectivity in the weighting values that are selected. So some more common examples of weighting in chemometrics: PLS utilizes weights as part of its actual algorithm. And then the wavelength selection, you can interpret that as weighting, where a rejected / a retained wavelength would be represented having weights of 0 and 1, respectively. So what are the current offerings of weighting in IoT? They are really limited. So it's basically just wavelength selection, and then there's one paper that's like a printout for a conference it's a pretty complex method. And that's basically it. But we would really like to, in IoT, take advantage of weighting to do prediction bias correction. So with that, I'm proposing the automatic wavelength weighting IoT. And this is based on some previous work that I did, a previous method I developed called Wavelength Angle Mapper, which is a calibration-free wavelength selection method. So basically, the steps are: first, identify your target analyte, API, that's pretty straightforward. Identify the wavelengths relevant to the target analyte using a spectrum of a mixture sample. So this is, you take your mixture spectrum and you apply the wavelength angle mapper. And I'll talk about each of these individual steps in a moment. So you have your map. So in this case, it would look something like this for a spectrum, where the blue is retained wavelengths and the red would be rejected wavelengths. And then you manually set the weighting values. So there's only 2 weighting values, because this is basically treating this as wavelength selection. So P is your upweighted values, and N is your downweighted values. So retained wavelengths get the P weight, and rejected wavelengths would get the N weight. Only weighting scheme of uses only 2 values, similar to wavelength selection, as I said. And we can summarize the relationship between P and N as just the ratio between those 2. And then we apply the weights to the squared wavelength residuals. So these are actually applied during the optimization process. And I'll show what that looks like in the mathematics, but it's applied during the optimization. So what is WAM? So WAM basically measures the angle of similarity, which is omega, between the individual wavelengths of the target net analyte signal for a target analyte, which is this net analyte signal is derived from the pure component spectra, and then the actual mixture spectrum that's going to be weighted. And then basically it sweeps a single wavelength at a time across the spectra to generate the actual selection pattern. So when there's a match in the shape, the wavelength is retained, and when there's a mismatch in the shape, the wavelength is rejected. And so you can see the wavelength selection that you would, if you were using WAM for wavelength selection, you would see the regions that are retained and the regions that are rejected. So pretty straightforward, pretty easy to implement. So AW takes advantage of that to identify what regions we actually want to apply weightings to. And so here's the math. So just starting at the top, I'll show a simplified math, but I like the numbers. So here's the actual IoT algorithm. So just a note here when we translate that over here. But you see, this is the actual optimization, and the weighting function actually gets applied right here. And I'll show that in the next slide. But here's our WAM method. So this is how you calculate that NAS target from the pure component spectra. And then this is what you actually calculate as your WAM selection. So +1, the wavelength is relevant to the predicting the target analyte, and -1, the wavelength is not relevant to predicting the target analyte. Those are you who are familiar with some of the math structures. This is just the cosine similarity calculation. So then we do AW weighting. So based on if the wavelength is positive relevant, it gets the P weight. And if the wavelength has a WAM that is negative, you apply the N weight, or you can express that linearly as this equation right here. And again, those weights are applied on a per wavelength basis. And then the weight ratio, which is just a little bit more convenient for graphing the results. And so here's the actual rewritten IoT algorithm, and you can see here how the WAM, which this is the linear, the AW, this is the linear form that gets input here. Same kind of assumptions and stuff, but a little bit more complex. So, demo of AW. So this data probably looks familiar to you. It's the same data that Owen presented, just reinterpreted using AW. So some values I'm going to point to: RMSEP, standard regular prediction error, the bias of of the predictions, and then this is relative bias. This is the change in the prediction from AW weightings relative to the original IoT predictions. So just to give another point of comparison. This is just the collection details. Our labs don't look like this. They're not that fancy. But we use the DA with the Centro blender. I believe this was taken at last year's meeting. PAT meeting, not user meeting. So here's some initial predictions just showing how AW actually interacts. So we got the ratio up here, we got the weight, what actual weights we apply, and basically we see kind of what the trends we would expect, both on the high dose and the low dose. So our target analyte was API, of course. Here's the pre-processing. And so if we look at base IoT, there's our predictions, obviously no relative bias. When we use a weight of 1 for each parameter, you see there's no change in the predictions. That's a good sanity check. So that's what we want. When we do AW IoT and we have the weight ratio equal to 5, you can see there's a positive bias change fairly significantly. I'll show some optimal models later, but obviously this overcorrects the error, and then this increases the error, frankly. But we can see it changes to a negative relative bias, and the overall bias is more negative relative to the base IoT. And then same trend we see on the low dose data. So here's just what that same information just presented in a different way. You can see here's the weight at set 1, which is the same as the base IoT increase when WE is equal to 5, positive bias. When W is equal to 1/5, negative bias. And then same thing on the low dose data. And so here's the trend at various weight ratios. So you can see we did from 1,000 to 0.001, and you can see it has this asymmetric sigmoidal curve. But as you increase the weight ratio, the bias correction approaches the WAM, what the WAM relative bias would be, which makes sense if you think about it. WAM would be P is equal to 1 and N is equal to 0. Or alternatively, yeah, that's right. So, and then low dose, same thing. It's pretty interesting. You'll note that the actual like degree to which the relative bias changes looks pretty different between the high dose and the low dose. I'll comment a little bit on that later, but basically a little bit of a spoiler. At low concentrations, the WAM method struggles to find the actual API peak in the actual mixture, so it doesn't always select all of the relevant API peaks. So since we're actually applying this to the residuals, it's useful to actually look at the residuals and see what's happening. So here's the high dose. So the gray regions are the relevant wavelengths, and the white regions are the non-relevant wavelengths. And this is the pre-processed data. And you can see, especially if we focus right here, you can see how base IoT, that's where it sits. Increasing the positive moves the residual towards 0 because it's more emphasized during the optimization. It's moving toward the actual pure component peak. And then when we have 1/5, which is we're emphasizing the regions where there's the non-relevant regions, it's increasing the residual in that particular region. And then here is low dose, and you can see the trend stands in most places, but for example, right here, which looking at the pure components, we would expect that to be a relevant peak, but for whatever reason, the WAM didn't catch it here. And so because this is a relevant peak, just by emphasizing the other relevant peaks, we see that same trend manifest. So just examples of how this algorithm is working on the actual residuals during the wavelength selection, or sorry, during the optimization. So here we actually get to some optimal models. So the original base IoT has a slight negative bias. You can see that in 4 of the 5 samples, 4 of the 5 test samples. And so with WAM, we overcorrect it so that we have the positive, and again, we can see the weight ratio is 1 to 0, 1 over 0. So it's a little bit of an overcorrection, but when we have a weight ratio of 5 over 4, we're able to improve the RMSEP, the R squared stayed the same, and we fix that bias. So it's a small correction, but it's still a meaningful correction. Similar thing with the low dose. You'll note that the bias is extremely small for this particular data set. So while we do have, it's a very small weighting that it doesn't really change the RMSEP, but it does change the bias a little bit. So there is one of the things of consideration with AW at this time is maybe not as useful for low dose data. And then this is what I call the dramatic example. So here's the base IoT, very clearly a negative bias. WAM again overcorrects the data, but when we apply the AW at a weight ratio of 3 to 1, we see a significant improvement. This is almost as good as the previous optimal model with our optimal pre-processing and a major correction in the bias. So just an example of how this could be helpful. So obviously this is a brand new technique, so there's lots of open questions. I won't read all of them, but I'll flip through them here and just highlight some of the major ones. So for example, the sigmoidal trend curve, given the challenge at lower concentrations, that it's expected that if and when WAM misses signature target analyte peaks, the relative bias trend would invert. So is the current bias calculation the best estimate of bias. So obviously, one of the things is that we're trying to move away from increasing calibration burden. You would probably still need some samples to find your optimal. So it does increase the calibration burden a little bit, but the simplicity of the method, I think, outweighs kind of the increased calibration burden. You're basically going from 0 samples to maybe like just a few more. Certainly easier than adjusting for PLS, or cheaper rather, I guess. And could we actually figure out what the relative bias trend would be for awe before we even do predictions? So, and obviously, and other questions that require an expanded data set. So this is just preliminary results, but we're hopeful that it might have some interest to people. So in summary, methods for weighting the wavelengths during the IoT optimization are potentially advantageous predictions by reducing noise interference, enhancing relevant signals, and for the purposes of this talk, correcting prediction biases. AWE is a proposed method of weighting the wavelengths for IoT algorithms derived from the WAM wavelength selection method that is able to automatically apply predefined weights to relevant and non-relevant wavelengths of a target analyte. Important note, AWE is not intended as a replacement for good pre-processing treatments. And the AWE IoT method shows promising results with expected data trends for NIR analysis of pharmaceutical blends. Thank you very much for your time and attention. I'm happy to take any questions.
Thanks, Adam. This closing slide came quite surprisingly. I was just organizing stuff for tomorrow, so no worries. One comment from my end. I can only speak for myself, but math in simple terms is a relative one. Thanks for a great talk. We have time for 2 or 3 questions. Owen?
Thanks, Adam. Really good talk. I have a question for you since you're something of an expert in IoT. Let's say someone said that PCA and PLS were the only methods you should ever use in the future. What would you say to that?
I would say, so yeah, that is a great point. I think it's all in context. If you're early in the feasibility stages, you don't have that much API, IoT is going to be a little more appealing because then you don't have to do a full calibration design to run your proper PLS or PCA. Also, at least with pure component methods, it doesn't cost you anything to test them out at the very start anyway. So I think as part of a good PLS development strategy, you probably want to collect your pure components. That helps inform your pre-processing, that helps interpreting loadings and that kind of stuff. And you already have the pure components. You might as well use them as part of some kind of modeling strategy. So to just say that you might only need PCA and PLS, but IoT and these other methods can still be really useful. I think it's overstating. Brad.
Great question, great answer. I have some thoughts here, but okay. Martin, give me a second. I'm not as fast as I was in the morning anymore.
I guess I'm looking at the weighting correction in terms of spectroscopy.
Mm-hmm.
We know from spectroscopy that there's a clustering effect between first, second, third overtones.
Yes.
So surely the weighting should follow that clustering. You should have a stepwise weighting. If you're trying to correct peaks that are second overtone versus peaks that are first overtone, it's a different correction than third overtone second. We seem to have lost the science behind the math.
Yes, I agree. I agree that a proper weighting approach, a fully fleshed out weighting approach would do that. That's a lot of what the weighting approaches are proposed. The idea behind this is that it's much more simple as a starting point. So I don't think that it's strictly necessary for somebody who is new to the field, who doesn't have that deep of understanding, if they're just looking for a mathematical correction just for the purposes of a feasibility study, I don't know that you need to go all the way to the very complex weightings. This is, as with IoT and CLS, it's more intended as a starting point, not necessarily like the final thing. This helps give some understanding to the data mathematically, and helps with, you can look at the trends in the residuals to try and understand specific things about your data. It's more of a tool to help. Does that help address your question?
Oh, 100%, and I'm totally in favor of IoT. I'm looking at it from the weight correction aspect.
Yeah, no, I agree. Yeah, again, the idea of this is that it's simple. It's only, I mean, technically it's only one weight because you can just use the weight ratio. That's really the intended. It's trying to make it simpler so that the subjectivity that comes with some of the weight, like I've read a lot of weighting methods that do a more scientific approach, but there still is that level of subjectivity in how much do you weight specific things. So this is just trying to simplify it. But yeah, I very much appreciate your question, and I agree with you at the end of the day. So thank you.
First of all, the choice of WAM as a term is kind of special. I was waiting for last Christmas to kick in every moment.
Yes, that was intentional.
More interesting, maybe because of the simple math you presented. Can you actually extract a reason why then certain wavelengths have been rejected? And is there some kind of like metric to say like these are rejected, like with confidence or something? I didn't get that really, but maybe it's just an understanding thing.
Yeah.
It would just look like a yes/no selection, but
it is quite, because it's only doing a single wavelength at a time. It's not like regions of spectra. It is literally just yes or no. So it's kind of how you would interpret the actual selection pattern is if the peak is actually visible in the actual mixture spectrum. So I do actually have a backup slide. Well, that's the definition of NAS. But this is like mathematically kind of just what you're seeing with WAM. Is it's only a single wavelength, so if the wavelength shape is present, if there's a match between the NAS and the mixture spectrum, you can see 180, or they would match a line, and that's +1, and if they are opposite directions, it's -1. So it literally is just yes, no, and that's what allows it to be, if you apply it for wavelength selection, you don't have to set any kind of threshold. That's what allows it to be calibration free. But you can actually look at the selection and see what regions you're actually grabbing. It is prone to sometimes grabbing noise just because of the random fluctuations in the noise. So certainly there are improvements to be made, but like as a starting point, it's useful for that. And I've had comments as I've presented WAM previously that it is useful as a visual just to understand your spectra a little bit more. So does that cover? Fantastic.
So just a quick comment regarding this. I like when people challenge PCA and PLS, but also as Brad said, this is something that people have done for 20, 25 years, and it is still the workhorse of the multivariate the PAT portfolio for understanding data and setting up in that way. And again, we do that internally as well. I mean, we develop software to make it easy for people to use. So we have to challenge ourselves as well, making sure that we test new algorithms, new twists, new way of making cross-validations and everything like that. And we do that on a daily basis.
Absolutely.
And still, what we implement into the software is something that we trust, that we think is transparent, but also giving the regards to the authorities in this case. This is something that is acceptable, and that there comes a trust from their side that we actually can use this in that setup.
Mm-hmm. So maybe I didn't understand. Like, was that just a comment, or was there actually a question? Okay. Just making
was
sure.
no
I
question.
appreciate that very much.
There was no question mark in the end. One very last comment from my end. On the closing slide, my name was indicated. Please don't contact me on this, Marv. It's a copyright slide.
Yeah, you told me to put your name up.
Yeah. No, I told you put your someone from Germany on. Just kidding.
I did.
Thanks again, Adam. Great talk. Very mathematical talk, but very interesting.
Yeah.
Thank you.
Thank you very much. I'm muting it for the next person.
Seems to be a bit of competition between the Chemometrics and MVDA guys.